So we have seen a couple different representations of a system of equations. We can write it as a system of equations. We could write it as an augmented matrix. We could write it as a vector equation. And today we're going to write it as a matrix equation. So again, the same thing with different representations. In this first exercise, we were asked to write a vector equation. So this is what we did last time. So we think about the coefficients of your x1. So I have a 1 in the first one, a 2 in the second one, and none in the third. And then 0, 2, 1, plus the coefficients of x3, which is -3, 9, 5. And that's equal to the right-hand side, which is 8, 7, -2. And then also the augmented system would look like this. So the coefficients of the x1 down the first column, coefficients of x2 in the second column, x3 in the third column. So there's the augmented matrix. So vector equation and augmented system. Part B says, look at this definition below and write the matrix equation AX equals B that is equivalent to the one above. So I'll let you look at the definition. I'm going to go through and write the A. So this AX, this first A, that's a column. So it's bold, so it's a vector, a column vector. And those are the coefficients of x1. Then you have the coefficients of x2. That is the A matrix. And then you're multiplying by the vector with your x1, x2, x3 equals the right-hand side, which is 8, 7, -2. So that is my A, my x vector, and my B vector. And then notice, so this another way to write that is this x1 times the first column. So this is the vector form. Another way to see this is that the x1s are the weights, and this is a linear combination of the columns of A. So that's just another way to see this. So B, the right-hand side, say this equals B, is equal to a linear combination of the columns. So I'm going to make a note that AX, this multiplication, a matrix times a vector, is only defined if I always say the inner dimensions agree. So it's saying the number of columns of A is the same as the number of entries in X. So let's look at some of these. It says, if possible, compute these. I'm just going to write down the dimensions. So this first matrix is a 3 by 2, and the second one is a 2 by 1. These inner dimensions have to match, so you can multiply it, so check. And then we're going to use this vector form. Our x's are the weights for the columns of A. In part B, again looking at the dimensions, I have a 3 by 2 and a 3 by 1. These inner dimensions do not match, so you cannot multiply those. This last one, I have a 2 by 3 and a 3 by 1. These do match, so I can do it. And again, think about the linear combination of the columns. Again, this x vector is my weights. So it's 1 times 8, 3, plus 1 times 3, 1, plus 1 times 1, 2. And if you add those together, you'll get 12, 6. The exercise says first use the definition above. It says then use row vector rule. So I'm going to erase these and do it again with the row vector rule. The row vector rule says I'm going to take row 1 and do what we call a dot product with the vector. We have 6, 5, and 2, 3. So it's saying 6 times 2, multiply your first two components, plus 5 times negative 3. That would be the first entry of your product. Then we're going to take the second row with this vector. So I'm going to have negative 4 times 2 plus negative 3 times negative 3. Then I have 7 times 2 plus 6 times negative 3. And doing it that way, we will get the same answer of negative 3, 1, negative 4. So I just wanted to point out both methods. So I would go ahead and in part C, try to work that out. Again, the first part would be take, again, we call the dot product between 831 and 111. What that dot product looks like is 8 times 1 plus 3 times 1 plus 1 times 1. In this example, we're asked to write the following vector equation as a matrix equation. And then what is the corresponding system of equations? So the matrix is the columns. You're multiplying by this x vector. And I wrote x's instead of z's, I'm sorry. So that is the matrix equation. And then the corresponding system of equations, the first one would be 2z1 minus z minus 4, z3 plus 0z4 equals 5, and negative 4z1 plus 5z2 plus 3z3 plus 2z4 equals 12. In example 4, we are asked to find the solution of ax equals b. So we're given A, and we're trying to find B. So A is a 2 by 3 matrix, and B is a 2 by 1. So my x, I have to multiply, these inner dimensions have to match, so this has to be a 3, and this can be a 3 by 1. So I have 1, 0, negative 3, 1, negative 5, 1. I'm going to augment that with my b. It's saying find the weights of this linear combination. If I row reduce this, I will get 1, 0, negative 2, 0, 0, 1, 1, 9, 3. So I can see that this is a free variable. x3 is free. And then x2 is 3 minus x3, and x1 is 9 plus 2x3. So if I were to write the solution for that, I'd have many different forms of this. The solution of this will be 9 plus 2x3, 3 minus x3, and x3. And another way to write that would be 9, 3, 0 plus 2, negative 1, 1 times x3. So sometimes it's not clear what form you should put it in, but this would be the parametric form, and reminder that's an infinite number of solutions because we have a free variable. So use the solution we just found to express B as a linear combination of the columns of A. So I need to find one particular solution. Need one solution. So if I let x3 equal 0, I could use 9, 3, 0. And that tells me that 9 times 1, 0, plus 3 times negative 3, 1, plus 0 times negative 5, 1, will equal 0, 3. So this is part of the theorem we mentioned before, where we have all these things are logically equivalent. So if we know one of these pieces, we'll know all the others. So in other words, if we know the columns of A span Rm, then we know that A has a pivot in every row. It means we also know that each B in Rm is a linear combination of the columns of A. So all these things tell us the same thing about a matrix. And I just want to point out that when they talk about this theorem, this A right here in the theorem is a coefficient matrix, not the augmented matrix. So just as an example, if we have an augmented matrix, A with B has a pivot in every row, then the matrix AX equals B may or may not be consistent. So again, these are two augmented matrices. If I get this last row, notice there's a pivot in every row, but that means no solution. So the theorem only applies to the coefficient matrix, not the augmented matrix. Exercise 5 asks, do the columns of A span R4? So that refers to this part, the columns of A span Rm, here M is 4. That would be the same thing as saying A has a pivot in every row. Well, A does not have a pivot in every row. We can see the reduced form. There are only 3 pivots. So because there's not a pivot in every row, the columns of A do not span R4. Exercise 6 asks, given A and B, write B as a linear combination of the columns of A. So in other words, we're trying to find our weights, or our x's. So we need to solve AX equals B. So I'm going to augment it. And when you row reduce this, we get 1, 0, 0, 0, 1, 0, 0, 0, 1. And the right-hand side is 0, negative 3, 1. So that tells me that x3 equals 1. This says x2 equals negative 3, and x1 equals 0. Those are my weights. So 0 times the first column plus negative 3 times the second column plus 1 times my third column will equal this negative 2, 2, 9. Exercise 7 is very similar. It's giving you vectors v. They are in R4. They have 4 components. And it's asking, can you write 3, 0, negative 1, 2 as a linear combination of those v's? So same kind of thing. We're trying to find our weights. So writing this in augmented form, the columns, and I'm going to augment that with 3, 0, negative 1, 2. When you row reduce this, get 1, 0, 1, 0, negative 1, 0, 0, 0, negative 1, 0, 0, 0. And then right hand side of 3, 0, negative 4, negative 2. This last row tells me that 0 equals negative 2, which is no solution. So we cannot write 3, 0, negative 1, 2 as a linear combination of the v's. And finally, this last question, does v1, v2, v3 span R4? In other words, can every vector in R4 be written as a linear combination of v1, v2, v3? No, because we just saw in part A that the vector 3, 0, negative 1, 2 cannot be written as a linear combination of those 3 vectors, which means that there is at least one vector that cannot be written as a linear combination, so it does not span R4.